Okay, we are looking at Chapter 6, the normal distribution again, finishing up today. We've already covered these 4 objectives. Well, now we're looking at number 6.4, the normal approximation to the binomial distribution. We've covered these objectives, and what we're doing now is objective 7, using the normal approximation to compute probabilities for a binomial variable. Now I want to go back before we go forward and talk about what we learned in chapter 5 about what a binomial variable is. A binomial variable is a variable that has 2 possible outcomes. It's going to be a success or a failure. And some of the things we need to remember about that is that we used P. Let me go back. I didn't have my pen on. Let me get my pen on. We use P when we're talking about the successes. That's the probability of, success. If you remember that from chapter 5. Okay, so P is the probability of success, and Q was the and I didn't spell that very well, did I? Let me go back. I talk faster than I can write. Okay, so that it makes sense if you go back and look at this. Okay, probability of success, and Q is the probability of failure. And we'll see this hopefully better as we work a couple examples. So we have the probability of success and the probability of failure. N is the number of trials. Okay, N is the number of trials you'll be dealing with. And X is the number of successes in those N trials. X is the number of successes in trials. Okay. Then we learned how to calculate some things that you'll need to use for this particular exercise. We learned that the mean was N times P. So you need to go back and write these in formulas you'll need to know for this test coming up. And sigma, the standard deviation, is the square root of N times P times Q. So those are things that we'll need to know as we go forward and talk about how to work the problems in these involving these binomial variables. Okay, so let's go on to the next slide. In this normal distribution can be used to solve problems that have a binomial distribution when N is large, 100 usually or more. It might not be 100, but there's some things that we have to do to check whether or not we can use the binomial distribution to calculate, our normal distribution to calculate the information on a binomial distribution. Now, what we have to know specifically and what's really important is the first thing you have to do, you're going to have to check right here this N, that N times P is equal to 5, and that N times, or greater than or equal to 5, and that N times Q is greater than or equal to 5. Those are going to be very important numbers. If they're smaller than 5, you're not going to be able to use it, and you just have to say, you know, we can't use the normal approximation to get information on this binomial distribution. We will learn how to do a correction for continuity. That takes a little getting used to. It's not terribly hard, but it does take a little getting used to. And the continuity correction factors means that for a specific value of x, you go on either side of that to get a boundary to include it. So if you're looking at 8, then what you're going to look for is you're going to go from 7.5, a half below and a half above, to get that continuity correction. And that's what takes a little getting used to, is knowing how you're going to do that. Okay. Now, this is what's confusing, but you'll probably use it later as you get to know it. Again, these are the formulas I just told you that were important back on the first page. So remember those. Get them in your memory banks. These are the continuity corrections. If x is equal to a number, you're going to go a half below and a half above. If it's greater than, then you're going to go a half below. And let me try to show you why. I'm not sure I can. But if you look at your normal distribution here, okay, and you've got a value you're checking here. This is A. And we're checking that x is going to be the probability of being A. What we're going to do is we're going to go a half below, and we're going to go a half below, above. And so you're going to actually find this shaded area in here between them, and that's not, my highlighter's a little wide, but you're going to find this shaded area in a range around that value you're looking for to get the probability. Then if your actual value is, you're looking for the area, here's your A, your normal distribution, and you're looking for your value A here. But you're really looking for all this above it, okay? You're going to go just below that in order to include A as part of that range, a half below it, and then you'll find all this area from this point forward when you're finding your z-score. When it's greater than, not greater than or equal to, then you don't, since it's not equal to A, you don't want to include A. So instead of hitting right on it, you're going to go to that half value that's just above it, because when it's greater than, there's not a line underneath it right here, then you don't want to include A. So you're going to go above it and not include A. So this is A plus 0.5. This would be A minus 0.5. And then it's the same idea here. That one is a less than or equal to. So if I was looking for a value A here, okay, I'm going to add 0.5 because I want to go less than, and it's less than or equal to, so I want to include A in that when I find my value. And here it's less than or equal, or it's just less than A. So in other words, I wouldn't go above it because I don't want to include A. I'm going to go below it. So it's not really critical that you know these formulas exactly, as it is why you include A sometimes and you don't include A sometimes, and whether you go 0.5 above it or 0.5 below it to find your z-score. And like I said, it takes a little getting used to, but it makes sense once you get to that point. So here's a procedure, and this is in your book. Check 1. First you see if you can use the normal approximation. Find the mean and standard deviation for your data with the information that you're given. Write the problem using X with your probability notation. Then rewrite the problem using your continuity correction factor. You're going to subtract sub-half or add a half. And then you're going to draw a normal distribution and try to show for yourself what the information you're looking for. Then find the z-values and find the solution. So that part, 5 and 6, is what we've been doing all through this chapter. So here's a few examples. This is 616. A magazine reported 6% of American drivers read the newspaper while driving. 300 drivers are selected, so that's your N. Okay, so 300 drivers is your N. So let's, we can highlight that. Okay, that matches. If you highlight, sometimes that helps. 6% is your success, so that's your P. Okay, that means if your failure is 0.06, we subtract from 1, your failure is 0.94. So that's your Q. We got that. The way we got that was to do to do 1 minus 0.06 is how we got that 0.94. And we want the probability that exactly 25. So for the exactly 25, what we're going to be looking for is P of X equals 25 when we get the probability, because we have this word exactly there. Say they read the newspaper while driving. So first, step one, if you remember, can we use the normal approximation? Well, that's our N times P. So we have 300 times 0.06, that's 18. N times Q, 300 times 0.94 is 282. This is what we're shooting for. They have to be greater than, both of them, greater than 5. If we are, we can go on with the problem. If they're not, we stop here. So find our mean and standard deviation using those formulas for the binomial distribution. N times P, 300 times 6, our mean is 18. And our standard deviation, the square root of NPQ, is 4.11. So that's step 1 and 2. Going on. We write the probability in probability notation. I already did that on the page before here. Now we use the correction factor. So if you remember, let's just draw a curve. Okay. Our mean is 18. So at the peak of our curve, we have our mean, which is 18. So 25 is somewhere up in here. 25. All right, but remember it's equal, and we've got to surround that. So we're going to use the correction factors. We're going to go 0.5 below it, right here, and that would be 24.5, and 0.5 above it, which is 25.5. So that's where these numbers come from, right here. Okay, below it is 24.5, above it is 25. So we've sandwiched it in with our value between those two. And what we need to find area-wise is this part that includes our average, our number we're looking for, not our mean, between those correction factors. So then we have to find a z-score that corresponds to the 24.5 right here, and a z-score. So we'll have a z-score here on one side of the 25 and another z-score here above the 25. So here's our z2 basically and our z1. We have to find two z-scores. And remember, our z-tables find to the left, so this one will find all this area to the left. When we read our table, this will find all this area to the left of z2. So to get what's between, I'm going to end up having to subtract z2 minus, or not z2 minus z1, I'm going to have to subtract the area that we find using z2 minus z1. So we go to our tables, we find out we have, x minus mu over sigma, and we get a score of 1.58 here and 1.82. So then we go down to our table. Okay, 1.58 is right here. Read over from 1.5 and down from 0.08, 0.9429 or 30, and 1.82 I think was the other one right here, 0.9656. And we'll go back up and, they found that data. 0.9656 minus 0.9429, subtract the 2 like we showed on our graph, and get the area between the two values, which is 0.0227, multiply by 100 to get the percentage, 2.27%. So the probability that exactly 25 people read the newspaper while driving is 2.27%. All right, so let's work another example. Here, of the members of a bowling league, 10% are widowed. If 200, and remember we're looking for fairly large sample sizes, 200 bowling league members are selected at random. Find the probability 10 or more will be widowed. P is 0.1. So we got that from this number. Okay. Q then will be 1 minus 0.1 or 0.9. Okay, so that's Q. N is 200. Okay, that's our sample size. And we want the probability that 10 or more will be widowed. So our probability is going to be, whoops, let me change colors so you can see it a little better. Okay, our probability is going to be a probability that X is going to be greater than or equal to 10. That'll be our probability that we'll use in step 3. So first we check to see whether we can use a normal approximation, N times P and N times Q, and we come up with 20 and 180. And remember, 5 is the number we're shooting for, so we're good as long as it's bigger than 5. Then we go on to step 2 and calculate our mean, N times P, get 20, and 4.24 is our standard deviation. We'll use those then when we're calculating our z-scores. So we'll go on. Here's our probability that we just came up with on the page before. X is greater than or equal to 10. We're going to use the continuity factor. And why did we use this one? Well, let's draw our picture again. Always draw a picture. That really helps. Okay. So our mean is here at 20. And in z-score speak, that's a 0. Well, we're down here at 10. Or the data we're using is at 10. Okay? And we want greater than or equal to. So we want all of this. Because of this line under here, we need to include the 10. So we're going to go 1/2 below it right here when we do our correction factor, which puts us at 9.5 because we want to include the 10. So X is greater than 9.5. We find the z value, was just 1 this time, and that's negative 2.48, 9.5 minus 20 over the standard deviation. So we know we're going to get to the left of it. What we're going to get, the information will be to the left. So we're going to have to subtract it from 1 to get this information. So what we find is negative 2.48. So negative 2.48 here, 0.00657. Okay, and if my curve was gone, but remember, we were looking down here, and what I found was this is 0.00, and they said 66. Okay, so the whole area is 1, so we're going to do 1 minus that to find here. So all this area here is 0.9934. So to get above 10%, remember we had our correction factor too. This was 9.5 we were looking at. To get our area that's above it, which is what we're looking for, we end up with 0.9934 or 99.34%. So if you make it a sentence, the probability of 10 or more widowed people in a random sample of 200 bowling league members is 99.34%. Now I put one other example. That was all that was actually on this PowerPoint. I put one that I think is probably in your book, but I just thought we'd walk through it totally by hand. That might be a good thing to do. So we have a baseball player's batting average is .320. Find the probability that the player will get at most 26 hits in 100 times at bat. So first we have to check to see first we're going to need to identify our variables. So we have n is 100. That's 100 times at bat. P is going to be equal to 0.320. And then Q will be 1 minus 0.320, which is 0.68. Okay? So to check to see if we can use it, we have to do N times P, which is 100 times 0.320. And that gives us 32. Okay. And then we do N times Q is 100 times 0.680. And that gives us 68. So they're all greater than 5. So we can use the normal approximation. I'm left-handed, so my check marks are backwards. Okay, so we've done step 1. Step 2, we have to find the mean. Mu is N times P, which we've really already done, and that's 32. And our sigma is the square root of N times P times Q, which is the square root of 100 times 32 times, or 0.32, excuse me, times 0.68. And that comes out to be the square root of 21.76, which is 4.66. So now we've got our mu and our sigma that we can use for calculating our x. What probability are we looking for? Well, at most 26 hits. So in other words, it can be 26 and it can be less than 26, but it can't be more than 26. So our probability is that x is less than or equal to 26. All right, so let's draw a standard distribution curve, our normal distribution curve. We locate our mean at the peak, which is 32. Okay, and 26 is somewhere on this side of it. Okay, but we don't remember, we have, because it's binomial, we have to get that correction factor. We're looking for less than or equal to 26. So we need to include the 26. So this time we're going to go to the right of our 26 with our correction factor. So that's going to actually be at 26.5. It's above 20, between 26 and 32. So this value here is actually 26.5. And we need to go all the way over here when we calculate our area, because we don't want to include the 26, again, because it's less than or equal to. If it didn't have this equal sign, we would have gone on the other side and done 25.5. So 26 was not included. All right, so what we're actually looking for is the probability that x is less than or equal to 26.5. That's what we're actually looking for. Now we have to find the z value. So we have z, and our x we're looking for is 26.5 minus the mean, which is 32. All of that over the standard deviation, which is 4.66. And when we do that calculation, we get negative 1.18. Now the unfortunate part with all this is when I have to go to another slide to look it up. Let's just look it up in the back of the book, the z-score. Negative 1.18, if you'll go in the back of your book. Okay. will give you an area. It gives you the area to the left of the curve. I'm looking in my book. Okay, and that's 0.3810. So this area, again, I'm looking at the left of my z-score for 26.5. I'm going to draw this down here is negative 1.18. So the area to the left of that is 0.3810. Okay, that's this area to the left. If I wanted greater than, of course, I'd have to subtract it from 1 and get the area here on the right. But the z-score always tells me the area to the left. So that's all I need to know. Well, I think my chart's wrong. I'm going to erase and go back just to double check. It was negative 1.18. I'm using an old chart, so I'm going to go back. Okay, here we are, negative 1.18. Yeah, that's wrong. Okay, 0.11900. 0.11900. The chart I was using only did halves. It didn't do the whole thing. So 0.11900, excuse me, is what we're looking for. So I'm going to go back, and all that was gone. But our probability that x was less than or equal to 26 was 11.9%. Okay, it's 0.1190 is what we read from the table, which is 11.9%. So I hope I didn't confuse you too much with this last example. If you have any questions, let me know. And your test, I believe, is coming up next week. So hopefully you can close out this section and be ready for a really good test.